Hey, hello everybody. We are live again. Today is July
Seventh.
7th. So we're here to report on how we're doing. I had the most productive day ever, and I'm sure my dad went backwards and threw half the book away, right? No.
I didn't throw anything away, but I didn't get a lot done either.
Oh, good. Well, that's all right. I did today. I did lots of graphics with light. I did transparency. I did reflection. I did opaque uh, with our light model. I did a couple of diagrams for, and I wrote the entire section for Infinity and not Yonel Dunu, but for Borkert. So it was
Well, you did
quite a
well.
lot. Yeah, well, it sounds like a
Thank you.
lot.
You picked me up, picked up my
Oh, I know. Dad works
loss.
on it every day, so I'm on vacation working on it. So that's pretty good. So I was pretty happy with it, working on the graphics and the words. So next up for me is going to be um, going through, oh, and doing the prism, like the dispersion. I want to do that one. So I'm sort of on all the light ones. I'm redoing all those that we had done before. So, so what did you not do today?
I worked on the diode today,
Oh,
but
can you explain people what a diode is?
yes, it's a semiconductor component that conducts current in one direction but not in the other.
It's like a one-way street, right?
Yes, it's so to a circuit electrical engineer that I did. It's not mysterious to me, but what's difficult is I could never really get the flow of the article to what I wanted to say. I started and I didn't like it, and I changed it. Then I had to go back and I had a video on it. I had a video about five different videos on the diode, whether a laser diode, a photodiode,
Right.
uh, whatever else, a Zener diode. And this is only on the diode in the book. That's all it's going to be as far as the diode is concerned. But I had to remember because it has a very unique solution. So the audience may be interested in hearing this solution.
Or they do they need to read the
No,
book?
they don't need to read the book. Just listen to what I say.
Shut up, Dave. Okay,
No, no,
I'm kidding. I'm kidding. No, go ahead, Dad. Absolutely. We
okay.
gotta tease our audience
Yeah.
of
Anyway,
millions.
if you look at the thing that you have to show right up front, and I do that, is the IV, what's called the IV curve. Current on the vertical, voltage on the horizontal, and it has a very strange IV curve for a forward bias diode. It starts out flat with no change. You add current, but the voltage changes, but not the current. And then it hits the knee of the curve, and then it goes almost straight up. Doesn't matter how much current you pump into this diode.
It seems
In
to
the
hit a threshold.
it 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 doesn't. You don't lose more with a resistor. An IV curve for a resistor is a straight line.
Oh,
That straight line. The slope of it is the resistance. So a high resistance is and a low resistance, and so on. This is a diode, and you put more and more current into it, and the voltage drop across it doesn't change. That any other component, most of my, I don't know. I'd have to think about the transistor, but you put more current in, you get more loss. Not with a diode. So the question is, how do you explain that? Well, standard model does not even address the issue. They just talk about what it does, as usual, and they don't explain the curve. So I'm writing an explanation of why that happens. And it has to do with speed.
speed of what? No, it can't be due to speed. Speed is the same all the time.
Nope, nope. And I've said this about a magnet, just to refresh people who may have watched the magnet is a pretty big regular magnets you have pretty big. And when I explained the magnet in the video, and I don't know if I said it in the book, but as it comes in, the F2 G2 gravity on both sides is very strong. Got a lot of G1 particles. Got a very strong force right there. It causes it to accelerate the G1 particle as it goes while it's moving in until it gets to the middle. That's where it's going the fastest, and then it slows down because it has an opposite force the other way. Slows it down, then it goes all the way around, and it's its slowest up at its furthest away. Then it goes faster and faster, slower and slower. It isn't a constant speed. They're all doing that together. It's slower. The one 180 degrees out is out of phase. The point is, even a resistor, as you enter, but as you're moving through the first half, it goes faster, and as you move through the last half, it goes slower. Okay, that's theoretical. What is the actual number? I don't know. Okay, but with the diode, you have the same thing. As it goes into the negative terminal of the diode, it's got this strong F2. It has an F2 force. The strength of that force is based on how many G1 particles are coming through. It already has them in there, but you add them when you go in. Anyway, as the circuit builds, because in the particle model, the circuit just doesn't instantaneously pop into position. It builds cycle after cycle, and it's very fast, but it builds. So you got a few G1s, you got a weak force. You get more G1s, you get more force. You get a lot of G1s, you get a lot of force. So what happens is even though the number of G1s going in, that's the current. That's directly related current. More G1s, more current. More current, you should think there'd be more loss. But the thing is, that force pushes them faster going in, it slows them down going out. Because of the structure of the diode in that direction, it pushes them faster through the N type, which has little space, and it slows it down in the P type, which has more space. So it speeds it up the faster it goes. Now here's the analogy. The analogy is the asteroid going through our solar system. One that moves very slow is very likely to hit a planet somewhere. If it goes faster, it may be the same direction, the same size, the same mass, but if it's going faster, it could zip right through, not hit a planet. If it goes faster through the diode, the faster it goes, the less probable it hits. And it goes faster because you get more and more current, you got more G1s, you got a stronger force, it makes it go faster and faster. So you have a compensation, even though you have more G1s coming in, they're going faster, so you have less interaction. There's compensating effect, which generates this curve.
So you're saying G1 particles don't travel at the speed of light all the time?
I sure do.
Folks, there you go. That's a big thing about our model. So,
but the problem, I finally, what I just explained, I finally got in the first part of the diode section. But then I spent some time trying to relearn about it. I actually manually did a spreadsheet calculation using a resistor diodes circuit, which I may not get done, and by the time we publish it, I may have that done.
Okay.
Can actually put that in if I can do it. I've done it for the resistor capacitor, the resistor inductor. I've done it for resistors. This would be interesting, a resistor diode, which would actually show in the spreadsheet how this increase, but see, you have to put in the spreadsheet this increased gravity. As the number of G1s increased, you got to have an increase in speed. As long as you program that in, and you programming it in based on the logic of the system that I just described being true to what I'm saying is happening, I should be able to generate a diode curve that starts out almost nothing and then goes virtually straight up. Would be amazing to do that.
And so
You get all
the
excited.
standard model says what about this?
No, what they say is if you put a positive voltage here and a negative voltage here, the negative voltage attracts electrons. Is a positive. Well, it's all charge, pulling and mostly attracting. Plus attracts the negative on the positive side, and minus attracts the positive on the negative side, and they create a depletion range. That's probably all true. I can see it happening when you build it. There's going to be a depletion range in the middle. I could talk about doping, and I started to. I had a whole section on doping. I'm not going to put it in. I'm going to leave it out because it doesn't help. I don't need to use that so much. I make a broad statement that when it's doped negative, it's got not very much open space. Because the G1 moves through the circuit based on open space, not on the number of electrons or and positive ions and negative ions. That's not. It'll move easily through open space, but it doesn't move easily through one like a resistor where the probability is it's really what amounts to smaller space. And so I'm doing it on the basis of space, not on the basis of charge, because that fits our model. But they never even address. They show it to you. They got labels for this and a label for that and so on. But then it's all about this depletion range, and then they say, well, when you put a positive this way, it allows electrons to flow. When you do it the other way, it doesn't allow, because it has to overcome this barrier in the depletion range. That's their explanation. What about the curve, guys?
So in our model with a diode, because it's one way, so you can have the current go this direction, but it won't go this direction. What happens in our model if you try to go against the flow in a diode? Explain that to a person.
Number one, there's the first rule. The G1 particle passes through. Most of them pass through, period.
Mm-hmm.
If they don't pass through, there's no way to establish a reasonable current through each element in the circuit unless they all see about the same number. All these voltage variations are small variations around this very much larger number that's flowing. So number one, whether it's forward bias or reverse bias, you got a lot flowing through. Now what happens in the reverse bias is you're coming into the one that's wide open, and it has a strong force pushing it, accelerating it the other way through an open space. So these things are coming through clean. And then you have, it's going faster, so it still goes faster through the one that has less space, and it is being slowed down. But what happens is you ultimately lose very few, really small. There's a half a volt drop. It measures a negative voltage drop across the reverse bias diode. So it starts out even going faster, and therefore it gets through easier in general because it's wide open as it comes in. Whereas the other direction is it comes into a thick area. It's going faster, but it's just starting to go faster. So you lose a bunch here, but you lose very little through the open area, and that's where you get the
So
point.
the difference, so in general with a diode, if you have 100 going through either way, one way it's going to lose more than the other.
To be specific, I use 0.1 volts per G1. A forward bias diode will, once you get to the point where it breaks into this line, it's 0.7 or a little bit more. It does have a slope to it. .7 volts means 7 G1s are being lost. You can have 1,000 coming in, but you only lose 7 G1s, and you can push more G1s in there. You can put 2,000 G1s in, it's still only going to lose 7 because of the speed going through, because of the force pushing it more, and so on.
So a diode's purpose is like it's like a resistor, though. Why? What's the difference between
like they often. That's what we were talking. It's a variable resistor. We taught that in college. I learned that. So.
Oh, okay. So in a resistor, you.
But it's a variable resistor.
So when you go one direction in a diode versus another, it's different. Whereas in a resistor, it's the same.
Either way.
Either way. So you would let's say a resistor, you lose 7 this way, or you lose 7 that way. In a diode, you lose 7 this way, and maybe
lose one.
One.
Yeah.
It will lose something, but not as much.
Right.
So that's the difference. That's what the.
Yeah.
So it's really strange that you really have in the particle model shows that you have. You basically have a pretty good flow of G1s going around, and you're playing with very small numbers as to variations that we then use for useful tasks.
Yeah, and the small number comes from the battery. How many G1s does the battery put out each interval of time, whatever interval? I always use 1 cycle as interval of time. Going at speed c, generally, it'll take a nanosecond to go around a small circuit. Not very long at all. But the battery, if the battery, I always use a 9-volt battery, 1/10 of a volt per G1, that's 90 G1s out. You got to lose 90, but you may have 18,000 going through. And you're only going to lose 45 here and 45 here, and then you get the 90 back.
Yeah.
But you got that many going through, including the capacitor. They say the electrons don't go through capacitors. Our G1, number 1 rule, most of them pass through.
Now you're an electrical engineer for like 40 years at least, right? Probably, well, longer, even though you weren't working at it. I guess when you stop working as an electrical engineer, you don't stop being an electrical engineer.
No, besides once I retired, we worked 4 or 5 years with a small group.
So you've worked a long time in as an electrical engineer, and you don't seem to be bothered by all these kinds of things, meaning where you hear stuff or taught stuff. I mean, I guess there's 2 sides of it. One is, who cares, because the stuff works and you got to design your circuit.
I didn't need to use the physics to design circuits.
But it is interesting, I think, that they can't teach the physics of it because it really isn't there. Because when they start to talk about it, it gets so screwy.
Almost everything, whether it's a double E department, I took electrical engineering in a double E and in the physics department. And it's always the same thing. This is what it does.
Right.
We give it a name, we formulate an equation, we calculate problems, and if I can calculate the answer to the problem, I might pass the test. But they attempt to say something, I think, because they show how they dope the P junction and the N junction. And they tell you what works, but all they do is say, well, the N junction has a lot of extra electrons, the P junction has loss of electrons, so it's a lot of positive. It's all particle, it's all charge.
So if you really look at it, then the truth of it is that because we have no model for any of this, including, what's really amazing about our Model 2 is that it doesn't only treat electricity, but it treats magnetic fields, which are basically G1 particles getting into loops, orbits, right? They're orbiting.
Yeah.
And what really is going on is because there is no physical model for the physics side, they teach electronic components more from an empirical side, really. And so what could happen is
that's what Ohm's law is, and what electrical engineer ever spent 1 day without using Ohm's law?
So, but what can happen is if this model were to actually, people think this is a valid physical representation, especially of the circuits. Now all of a sudden you really have something to teach in the physics side, whereas you can still use the electrical engineering empirical equations. But this, I think two things could happen. One is, again, physics would be teaching a totally different thing, where they're talking about what we're talking about now and what we're putting in the book.
Yeah.
The second thing would be is that I think electrical engineers, when they would learn that in physics, then they could start thinking to themselves, oh, are there things I'm not thinking about in circuitry that are there that I'm not taking advantage of or could take advantage of?
Or are they hurting me?
Or are they hurting you, right?
Yeah.
Or can we even do new things with it because now we know really what's going on.
Yeah.
So that to me is really exciting. And I think for, and again, for those of you who don't know, go to Particle Guru. You can see right there, right there, youtube.particle.guru. Yes, .guru is a, like .com, it's but that's .guru. You can go there and subscribe to my father's channel. He talks about, he's got over 100 videos on the particle model. But I really do think that the electrical engineering side is quite exciting. In fact, a lot of the dissident scientists I know who I actually like, and again, folks, this is totally the truth. The people work outside the mainstream. There's a lot of people with different attitudes of how they look at things. Some people have the attitude, well, I've come up with my model. Everything I do is right. That's the only thing that's important. And then if you question anything or there's problems, they don't look at them. Or there are people who don't have their own model, but their idea, they're not, how do you say, they don't have this, what I call an engineering attitude. It seems like the electrical engineers are like Harry Ricker. I've worked Cat. I think he does a lot of stuff with electricity as well. But there's quite a number of people who are electrical engineers. And I really think that this book is going to be pretty fascinating to those people. And one of the things I'm going to be doing very soon is I want to finish the graphic for the dispersion. I need to do that one. Once I do that one, I'm going to start then on the battery, because that one's super fascinating. I think battery of all of it is pretty fast. I think.
Yeah, explaining the IV curve for a diode, that's such a strange curve. And one of the things I did during those 5 videos I did on the diode, there was one graph I found on the internet that showed, well, here's where the diode is forward biased, here's where it's back biased, here's where you use a Zener, over here is where you have photodetectors, over here is where and it's all the same curve. It's all the same technology. There was a graph I actually saw today of a chart of how many different diodes you could buy. It was a physical picture. Here's a round diode, a cylinder diode, a flat diode. Looked like there would be a 50 diodes in this one chart, just of different flavors of the same thing over and over again, and all from this one IV curve. It all fits in.
But it's just really playing with the numbers of how many G1 particle it goes through.
What's the size of each element? What's the doping? What are you doping with? Is it silicon-based, germanium-based? Gallium arsenide is the other one. These are all bases, and then you dope these.
Yeah, it's all done. People make these electronic components by trial and error, or people who know the chemistry, who try to put together things. But it's really more just a recipe, right?
Yeah.
I mean, that's really what it is. And they find things work better because you're really basically playing around with the flow G1, the flow through the G1 part. Do you have a lot of G1 particles, a lot of electricity, basically, right?
Yeah.
Or do you have little, and then how much do you need to block one way versus the other? But again, there's just no physics involved with it.
Yeah, and the transistors the same way. You've got bipolar transistors, field effect transistors. I said a lot of them. I just came up with only 2, but anyway. So I got to finish that, but I actually, the last time we had this video, I said it on Wednesday I was going to go back to the Eddington and Dowdy explanation and clean that up and finish it off. So I'm going to let the diode sit, and I'm going to go do that tomorrow and get that done.
I think another fascinating thing about the model, because when we talk about a model for the entire universe, it really is. I think one of the shocking things I find, and this, hopefully I will remember for this, for my impressions
Yeah.
part, one of the impressions I get is how these stupid, simple rules work everywhere.
Yeah.
I mean, we're looking at light and eclipse and gravity and magnetic fields and all of those things. It just, we're doing it routinely, but if I see a lot of other models out there that people have, that when you really look at things, that for some reason you don't see that happening. You don't see them applying it to all those levels. I think most of the time people are working on them.
I was too stupid. I just went ahead and
No, but I mean, I think most of the time when people have the models, and there's some nice models out there.
well, they have an application, but they don't visualize the broader use of it, if
Well,
there has a broader
I don't
use.
think that's what's happening. I actually think with other models, with other people, it's not that they're not thinking of that. I think they get caught up in the model, and they are really working on that model. And they do try to explain a lot of things with it. Like if you start with ether, the idea that lights waves through, where we have sound waves, we have ether is the idea that you have waves through this thing called ether, and that's what you make light. Even with those people, they spend all their time on how do I do gravity or how do I do other things. So they're really, really pounding on their own models in areas that they seem to not be able to go into.
To get it.
Yeah, they seem like, so they take hammers and then they hammer it, then they add more attributes or they add more shapes, and they sort of keep finagling and sort of keep crafting that model, and so they never get the time really to do large scale applications. And you think, and what you hear a lot of times is just,
Well, how do you apply ether to circuits?
well, I mean, the idea is that you would apply it because wires hold the waves.
Well, you can say
inside.
but you got to go further than the
Right.
statement.
Well, I mean, that's a good example. Is where we obviously use Borker a lot, and he was the one that inspired electricity being the G1 particles. But of course, we don't have the problem because our G1s can be totally guided easily by G2 gravity right through the nucleons. It's perfectly good. But when I asked Borkert about what electricity was, and he says, well, it's the same speed of light, then it's just waves that are confined to the wire. Now, that's an idea, and but the thing is though, why hasn't like a Borkert model or an ether model gone and done all those things?
So the first thing I did to go back day one was for the gravity experiment. I developed an equation for gravity. When I developed an equation for the circuits using G1 particles going through circuits, same math, simple algebra, B in, something lost, C out. That's the same thing I did for gravity, and so I've already written equations for gravity and for G1 gravity and G2 gravity, and they look identical except they are literally with G1 particles up here and G2 particles down there, and they're smaller and they interact different, have a different constants, which I haven't developed that part, but I'm not sure how I would yet.
But I mean, going back to this bigger question of why other models aren't doing this, I think not even to try to necessarily explain it, I just think it just shows that models don't have enough of the basic parts to be able to describe the whole universe. I think most models will start out in a small area, either like light, that's very popular,
Yeah.
and then they go from there, light and gravity, and then from there. For some reason, the parts that we put all together, I mean, look at our first year, what we were doing.
It's amazing.
I mean, we were not taking our model and pounding it to try to make gravity work with it, or we weren't trying to make a graviton. We had those answers. You gave that answer, and I think that's that's why it broke open completely, is because at that point you had one of the biggest questions out there is what could light be, and you gave a sort of new model for that, which is very simple to understand. And then we went to town. All we did then was start applying all these things to the universe, even though we didn't know what we do. If you read the first part of our book today, basically the first part of our book is wasn't there. We really didn't think about it too much.
No, because that had to build up.
Yeah, I
over
mean, we really
time.
didn't know what was going on. We didn't know what we had necessarily, how it all fit into a bigger picture. And even though we had the big picture, we were just hacking away. But I think that's a completely different thing that I've seen with other people. I think people, again, are there, for instance, a lot of them will model the atomic structures, right? That they go right away into modeling the atomic structures, and from there, then they try to fit in then light, and from
They're
there,
already in hack 4, but they skipped hack 1.
yeah, they forgot hack 1, 2, and 3.
Forget about getting a bachelor's degree. I'm going to get my doctorate.
That's
first.
right. Just go right to the doctoral degree. But I think that's really what happens, because again, I've seen some really good models. I'm not going to mention the names, but we know very very intense and very detailed models. One of them starts with the periodic table, and then from there, I think then they really try to figure out what's going on. But I think one of the problems is they all seem to have charge. They all seem to have fields, and they're always everywhere. So no matter what shapes you make everything, what shapes you make the electron, or what you think is going on, there's always a charge, and there's always a movement of charge, and the charges come together, and there are fields, and when you ask people what they are, they sort of throw it out there. This model just doesn't have that. I just
We're too poor.
I don't know.
No.
I think it's just amazing to me how people we're bouncing back and around, and it just, I mean, if you think about it, it's absurd, because you're talking about giving physical meaning to the electronic, the way it works, electrical circuits, down even a level that other people don't even have, like the G2 level. And then we bounce off and then talk about the eclipse, and then all those things. And we're just using the same model as if it's just, this is normal. So either or you and I are either absolutely in sync with our hallucination of madness, or there's actually something here.
Well, we finished the 5 years as of June 28th of this year. We've completed 5 years of work already.
Well, I think you came up with your part. Yeah.
I came up with mine earlier, but
right.
But I didn't do anything with it. I'm sitting here waiting for you to respond to me.
I think we have to put that. I have to put that in the book, in the forward or something, but maybe it'd be in the impressions. But your diagram of light.
Oh no! Wait a minute. You don't want to put my diagram in.
No, but I think the only thing I can say, there are two things that is amazing, because it was in my opinion, one of the great insights and models that whatever you want to call it, in science. I just think it's great. Your name is in history or in infamy. But the picture, the other thing I have to say is Dave D. Hilser is really good at visualization, because your drawing went by lots of people and no one saw it, even me, until you finally sort of described it.
Yeah.
So if you go from that one drawing,
Well, actually, if you remember right, the white paper I sent you, I said, I need to put a drawing here. And then I forgot and sent the paper to you, so there was no drawing. There was only words in that white paper. There was no drawing.
Oh, But you made didn't you make one with one?
Oh,
Oh
then
yeah.
I made some later. Yeah.
Oh yeah. I mean, it's like, where's my pen? I mean, it's
I had
really.
numbers like 3, 4, 5, 3, 4, 3, 3, 4, 5, 4, 3, 1, 0, 1, 2.
It was so funny because it's like this. I can draw. I can draw it. It's really hard for since I'm a graphic person. Here we go. You just draw a bunch of circles. I'll show everybody here. And you go 1, 2, 4, 5, 4, 2, 1. Now this was. Can we see it? It'll come through. There we go. This was my dad's first drawing of his model for light. Now, let me tell you what this really is. Now I'll draw on top of this. This is 1, this is 2, this is 4. I'll even do it this way. 1, 2. This is 5. This is 4. This is 2. And this is 1. This is what he really meant. And so what was happening was he was
drawing the peaks.
You were drawing the I don't even know what you were drawing. But basically if you look at this, and this is where I went nuts on the day that I understood this. If you look here, the wave that's light is basically all these particles are moving in the same direction, okay? They're all moving like this, all right? So they're all moving, there's the arrow, they're all moving together at speed c. So the 1, the 2, the 4, the 5, the 4, the 2, and the 1 are all spaced like that, and they're moving like bombers in the sky. You know, and once I saw that, I realized that is a solution to one of the biggest problems in all of science. Now, if you looked at the bottom part, let's see if I'll cut it off. There it is. And you don't see it there. But so I have to give myself credit for actually seeing what you from the, because this was the thing, your slide, right?
Well, it was one.
And then when
it was like that. I did it by numbers, not by.
Right, and then when you did, because that's why I didn't see it.
Yeah, when I did the peak, valley, you got that one.
Yeah, well, I got it, but I put it together because even the peak valley wasn't really a description of really what was going on.
Well,
this is.
Yeah, you got the peak and you got the valley, and of course, valleys aren't necessarily nothing. They could,
Yeah.
It goes to 0 and back up. Notice, however, there's no negative number of particles.
We're going to talk about that later. But folks, this was really good. Yeah, I've got to go, and I don't want to bring these two up, but we'll have to talk about that would be another interesting topic, is no negative numbers in physics. There are no such thing as negative numbers in the universe. Did you ever think about it, folks? We'll leave that thought with you. Today was really good. Some days our recordings are pretty out there, but this was pretty good. And I do thank people for coming by. We'll be here tomorrow working on our book. And remember, please do go to principiamathematica2.com. Sign up. I mean, you can go to that and read about our particle model. We have actually the table of contents there. We have the 4 classifications of particle movement, which really is the heart of it. If we were to make a T-shirt of our model, we would have those four particle movements on there. And make sure you subscribe to our YouTube channel, and also you can like our Facebook page. So thank you so much for your support, and we will be here hopefully every day during this week as we go. It's Tuesday, so we got Wednesday, Thursday, Friday, Saturday, and Sunday before I go back to my job where I make my money and make my living, which is also fun, but this is what this is all about. So thank you so much. Have any questions, always come by and ask us questions during our live sessions. We are announcing those ahead of time now, if you notice, so people can prepare when to stay away. I mean, when to come by and listen to us. Okay, guys, say goodbye, Dad.
Bye, Dad.
There you go.
I did it right this time.
Ciao for now. Goodbye. I can't get to the button because of our wide. Where's the mouse? Goodbye.